So, in the last class, we were looking at how one might take a prototype filter and then generate another type of filter. For example, you wanted to take a low pass filter with a critical frequency of 1 radian per second and generate another network where the critical frequency has been moved to some other frequency, right? And then we saw that all that it involves is transforming or replacing omega in the original approximation or the original network by some other function of omega, right? And therefore, it's equivalent to basically moving things around on the x-axis. Now, then we were wondering, can I choose, presumably there are many f of omegas which can affect the same kind of transformation that we want. So, for example, if you wanted to move a low pass to another low pass, replacing omega with omega by omega naught does the job. So does replacing omega with omega by omega naught the whole square or omega by omega naught whole to the power n, right? Then we saw that you just can't replace the omega with some random function of you can't replace it with a random function of omega. If you are interested in realizing a physical network, okay, which works. Okay. So what we then said was we have to replace. There is some conditions on the f of omega, and in other words, every reactance which is of the form j omega gets replaced by another reactance j times f of omega, which means therefore that a lossless element which is either an L or C in the prototype network is getting replaced by another combination of lossless elements, right? And since the only lossless elements we know at this time are inductors and capacitors, it thus follows that this f of omega or j times f of omega is simply the impedance of a combination of inductors and capacitors. In other words, j times f of omega is nothing but the impedance of a lossless LC network. So, studying the properties or the constraints that f of omega must satisfy is equivalent to studying the driving point impedance properties of lossless LC networks. Is this clear? Okay. So, a little bit of background is necessary to understand this. I will cover that background. The first, these are all preliminary, so-called preliminaries. The first is what is called Elegance Theorem. How many of you are aware of this? Okay, how many of you don't know this? There's no harm in not knowing. I'm just asking, trying to find out. Okay. Okay. All right. So I'll. So let me take an example of a network. The usual stuff drawn in the textbooks. Okay. The network has nodes numbered 1, 2, 3, and 4. I can choose any one of my nodes as the reference with respect to which all other node potentials are measured. Okay. So, a network consists of nothing but nodes and branches. I will number the branches. I will call the branches branch 1, 2, 3, 4, 5, and 6. Correct? So, this is what is called the graph of a network, okay, where the nodes have been circled and the branches have been numbered. Every branch is associated with both a branch current as well as a branch voltage, and at every node Kirchhoff's current law must be satisfied. So, let us write down KCL at every node. So, at node 1, what do you see? So, if I write it in matrix form, there are how many branch currents? there are 6 branch currents, I1, I2, I3, I4, I5 and I6. Okay, and at the first node, what all, I mean, let's keep the convention that currents flowing into a node are positive and currents flowing out of a node are negative. So, what is the KCL at node 1 quick? Minus I1, I2 doesn't show up. What about I3? 0, I4 1, I5 minus 1 and I6 0, right? Okay, so this must be equal to 0, isn't it? Now, what about node 2? Come on, people. 1, 1, 1, all others are 0. Must be equal to 0. All right. At node 3, 0, minus 1, 0, 0, 1, 1. Must be equal to 0. Correct? So, how many rows are there in this matrix? The number of rows in this matrix must be equal to the number of nodes minus 1, because one node's potential, I mean, we have considered to be the reference. Okay. All right. So, each row in this, each equation in the set of equations represents KCL at one of the nodes. All right. Now, let's observe the following. What do the columns represent? For example, what do you, I mean, can we interpret the columns of this matrix?
Which node to which node current?
Correct. So, basically these, so for example, if I pick some arbitrary row, a column of this matrix, this minus 1 comma 1 means that branch, which branch? Branch 5 leaves node 1 and enters node 3. Okay. So, these columns represent the branches and these rows represent the nodes. Does it make sense? All right. And those columns which have only one entry, okay, they are going to the ground. You understand? So, all right. Okay. Now, if I call this matrix A and if I call this column vector I, then A times I is 0, where 0 is a column vector of 3 elements. Does it make sense? This is nothing but KCL written at all nodes. Okay. All right. Now, given that we know where the branches are originating and ending, from the matrix A we can figure, we know, for example, that the fourth branch starts from node 1 and goes to ground, okay, or starts from ground and goes to node 1. All right. So, if one wants to find the branch voltages in terms of the node voltages, you understand, a branch is joining two nodes, correct? So, if you know the node potentials, how would you find the branch potentials? You need to figure out where the branch starts and where it ends and subtract those two particular node potentials, correct? Okay. So, in other words, the branch potentials or the branch voltages are nothing but, if I gave you the node voltages V1, V2 and V3, how will I find the branch voltages? Yes, the first branch voltage is what? It is V1 minus V2. Okay, so this is V1 minus V2 and 0. Okay, and so on. And what about the branch 2 voltages? What is the voltage across branch 2? V3 minus V2. And what is that? V3 minus V2 and so on. So what do you notice? So you see that this is nothing but minus A transpose. Correct? That makes sense because the columns of A are giving you information about where each one of the branches is starting and ending. Correct? And the difference between those two voltages, node voltages, is what constitutes the branch voltage. Correct? So, in other words, if V denotes the vector of node voltages, then minus A transpose times V is the branch voltage vector. Okay? V is the node voltage vector. Is that clear? Now, if I want to find the sigma of, let me say, VBK IK, where VBK stands for VBK stands for the branch voltage of the kth branch, and IK stands for kth branch current. Okay. What is sigma VBK IK physically? Is the power either depending on the algebraic sign, either dissipated or generated by the kth branch. So it follows, I mean, it's must be pretty apparent that sigma of all the branch voltages times branch currents must be 0. Okay, let's actually set out to prove it. So what is sigma VBK IK? It's simply nothing but the branch voltage vector VB the n branches, then this vector multiplied by I1, I2, IK, IN. Okay, this must be equal to is what sigma k VBK IK means, isn't it? All right. Now, what is this in terms of the matrix A? Minus A times V, the whole transpose. Correct? Sorry. Minus A transpose V, the whole transpose. That is this character. And what is this guy? Guy is nothing but I. Right? Which is nothing but minus V transpose AI. And what is AI? 0. Which means that this must be equal to 0. Does it make sense? What is V? V is the node voltage vector. So to get the branch voltages in terms of the node voltages, we already saw that the branch voltages in terms of the node voltages are given by minus A transpose V. Is this clear? Yes, people, yes, no, yes. Okay. And the product of the branch voltages and the branch currents, okay, and the sum of all of them is nothing but the branch voltage vector transpose multiplied by the branch current column vector. Okay. The branch voltage vector in terms of the node voltages is A transpose V. So that transpose times I is what you are looking for, which is nothing but V transpose AI, which is AI we know is 0 because all the branch currents satisfy KCL at every node, correct. So this is 0. Okay. So one might think, hey, what's the big deal, right? I would have told you this even without doing all this complicated looking math, right? The power at all instance must be, I mean, whatever, due to energy conservation, the power pushed out by each branch must all add up to 0. But the cool thing about this is that if you had another network, with the same graph, let's say you had network 1 and network 2 with the same graph. Okay, by meaning same graph, what I mean is that this network could be, for example, like this could have an inductor here, this could have a capacitor here, this could have a voltage source here, this could have, you know, and here there could be completely different elements. There could be, for example, a diode here, an inductor here, a resistor here, and so on. So these two, what is the commonality between these two networks? Both are the same graph. In other words, the A matrix for both these networks must be the same. All right. So now let's try and find sigma. So let me call this N1 and let me call this network N2. So if I try and find VB1K times I2 of K. Okay, I mean, we all know that sigma VB1 of K times I1 of K must be 0. I mean, for a single network we are not very impressed, correct. Now I am trying to find the sum of the voltage in, I mean, I will find the VI products where the branch voltage is that of network 1, but the branch current is that in network 2. All right. There is no physical interpretation for VBIK, I2K. You understand? So this must therefore be, can be written as what in terms of the node voltage vector and A and so on. This is nothing but minus A transpose V1, where V1 is the vector of node voltages in network N1, correct, and I2, which is the column vector of branch currents in network 2. Sorry, this whole transpose, correct. All right, and this is what minus V1 transpose A I2, but hey, network 2 has got the same graph as network 1. So A times I2 must be 0 because the currents in network 2 also satisfy KCL, correct. So this must also be equal to 0. right? Now this is quite impressive in the sense that it seems kind of what do you call funny that you can do this for two different networks, or for example the same network at two different times. There is absolutely no constraint. We have not assumed anything about the network. The network could be nonlinear, could be time varying, could be anything, right? All that we care about is both the networks have the same graph and KCL is valid. KCL is valid in both networks, which is of course a fundamental thing, and is true. You understand? All right. Okay. It gets even more curious, sir. Now, if instead of talking about the node voltages in the time domain, I could replace all these voltages and branch currents by their Laplace transform quantities, okay, and going through the same reasoning, right, there is no difference at all. You find that if two networks have the same graph, then sigma Vk V1k of S times I2k of S, okay, must be equal to 0. This is over. Does it make sense? All right. And of course, now once you start getting complex numbers, it if we know that if you replace, I could also, for example, replace this by their conjugates, and this will still be valid, because if AI is 0, then AI conjugate is also 0. So as long as both the networks have the same graph, this must also be valid, okay. And there is no straightforward interpretation of this either, okay. When you multiply two Laplace transforms, okay, it's not very clear what this means. No, if AI is 0, right, then if I take complex conjugates on both sides, A is, I replace every Laplace transform, I just take complex conjugate on both sides of the equation, correct? Okay, so the Elegance theorem is what we call a very versatile and intriguing theorem, which can be used to prove many things. For example, reciprocity in networks, right? All that stuff becomes very easy once you're aware of this. And please note that this is simply a consequence of Kirchhoff's laws. That's all. It's got nothing to do with linearity of the network. Okay, and therefore is a far more general thing, and so on. Okay, all right. Now let's get back to our stuff. I mean, the only reason I brought in S is because we are trying to figure out the properties of the driving point impedance of LC network. So it's an LC network. Let's. Pardon? Why?
I mean, one branch current would depend on the
That's okay, but as long as all that is involved is that the sum of the branch currents must be 0. This is true for any network. Please note, controlled sources, no controlled sources, everything. Okay, all right. Now let's say you have a lossless network with only obviously inductors and capacitors. We are trying to figure out what the property of the driving point impedance of such a network is, the motivating factor being the whole discussion on frequency transformations, right. So clearly for this network, sigma Vk of S times Ik star of S over all branches must be equal to 0. Okay. So the only branch for which the sign of these is negative is which one? Which one? This is the only branch for which the sign of Vk, Vk times I is negative, simply because I have chosen this to be a source. In other words, therefore, V1 of S times I1 star of S is sigma over all the other elements in the network, which are basically inductors and capacitors, because by construction we said the only inductors and capacitors in the box. Correct? So this must be Vk of S times Ik of S over all L and C. Does it make sense? All right. Now, what is V1 of S in terms of I1 of S and the impedance looking in? V1 of S is simply, by definition, Zn of S or Z of S times I1 of S. Correct? If you pump in a current, the voltage developed is nothing but the Laplace transform of the impedance looking in multiplied by I1 of S. All right. So this therefore means that mod I1 of S the whole square times Z of S must be what? Yeah. Thank you. Pardon? No, only a negative sign because I moved it to this side of the equation. Yes? Okay, that's what allows me to move the stuff to this side of the equation. Is that clear to everybody? Okay. So now I need to sum over all L and C, Vk of S and Ik star of S. For an inductor, okay, how do you relate Vk to Ik? If the kth branch was an inductor, how would you be able to relate the branch voltage to the branch current? This must be therefore for all L S Lk Ik of S times Ik star of S, yes, plus over all C what? Palni Rakesh, 1 by SCK, very good, Ik of S, Ik star of S. Okay, I have been a little loose in the terminology here. I am using the same K for both. Obviously, it means that, for all capacitors and all inductors. Now, this therefore means that mod I1 square of S times Z of S is sum over all L S times Lk times mod Ik of S the whole square plus sum over all C 1 over SCK mod Ik of S the whole square. K are nothing but indices which run over all inductors and all capacitors. Does it make sense? Now, therefore, and I am free to choose my excitation I1 of S. So I will just choose it to be 1, right? Which means that Z of S can be written as all L S Lk mod Ik of S the whole square plus all C 1 by S mod Ik of S whole square by Ck. Correct? Now, can you comment on what the sign of this quantity is? It is always positive, right? What about this? This is always positive. So, in other words, Z of S is S times P1, which is always a positive number, evaluated at when Z of S. So, when irrespective of the S at which you are evaluating, this P1 is always a positive number, okay, plus 1 by S times P2, where P2 is also a positive number. Is that clear? Okay. Now, let us stare at this function and make a couple of observations. The first observation is that Z of S must be real when S is real correct, and 2, Z of S must have, if S is complex, please note that Z of S must have a positive real part if S has a positive real part. See, P1 and P2 are both positive, correct? So, if S has got a positive real part, in other words, if S is a complex number and its real part is positive, then when you evaluate Z of S, it must turn out that the real part of, if S is complex, this must be a complex number, because P1 is real and S is, and P1 is positive and S is complex. Similarly, P2 by S is also a complex number. If S has a positive real part, the real part of S times P1 is also positive. Can you comment on the real part of P2 by S when S is a real, has a positive real part? S and 1 by S will always have the same sign for the real part, correct? So, it follows that Z of S must have a positive real part if it is evaluated at some S with a positive real part. So, this is a whole class of functions which are called positive real functions. Okay, and this is the basis of network synthesis. Is this clear? And this has got, this is very basically all, the starting point is Elegance Theorem or some kind of energy functions type stuff, because you can think of Li square as, for example, if you evaluate Z of S on the j omega axis, correct? What do you think will happen to, one immediate consequence of this is that if you evaluate Z on the j omega axis, what can you say about Z of S? It is purely imaginary, correct? Okay, this is something that you knew, all right? And if you evaluate S on the j omega, Z of S on the j omega axis, this sigma L I square stands for energy stored in the inductors, and similarly this stands for the energy stored in the capacitors, and so on, right? So, the whole starting point is an energy conservation like theorem. which we got from Elegance Theorem. All right. So, since we made the observation already, if only inductors and capacitors are in the network, Z of S is what? Is purely or real part of Z of S is for real part of S greater than 0, what is it? Is positive for real part of S greater than 0 is 0 for real part of S equal to 0 is nothing but the j omega axis, on which we know that the impedance is only imaginary. Then what about if the real part of S is less than 0, then Z of S evaluated at such an S will also be, the real part of Z of S will also be negative. Does it make sense? All right. Now that we know this, now if Z of S is a complex function and if it only consists of inductors and capacitors, in other words, if it consists of lumped elements, this must be of the form n of S by d of S, where n and d are polynomials in S. Correct? Now, from what we have just seen, this polynomial ratio of polynomials in S, when evaluated, let us say you are going from here to here along that path. Can you comment on the real part of Z of S? It will go from negative to positive. Okay. Now, if we can express a complex function as a ratio of polynomials, then it therefore means that the roots of d of S are the poles and the roots of n of S are the zeros. We already know that both the roots of n of S and d of S cannot lie in the poles and zeros cannot lie in the right half S plane. So the question is, where do they lie? All right. So a little bit of background information. If you have a complex function and if you go close to a pole, all right, and if the pole has close to a simple pole, let us say, how can you approximate the behavior of the complex function around the neighborhood of a pole? It's basically some number r divided by S minus P1, right? Okay. Now let's consider the behavior of 1 by S minus P1, okay, in the neighborhood of P1, right? So if S is very close to P1, geometrically where can I draw S? Somewhere, for example, here. What is S minus P1? I draw a vector from P1 to S. So this is nothing but S minus P1. So can you comment on the real part of 1 by S minus P1? What is the sign of 1 by S minus P1 as S goes around the pole? Okay, it depends on the angle. Very good. Okay. All right. Now,
This is positive.
pardon?
This is positive.
This is positive. So, in other words, if S is close to a pole P1, if it is to the right of the pole, the real part of 1 by S minus P1 must be positive. The real part of 1 by S minus P1 to the left must be negative here, and when it's on the j omega axis, the real part must be 0. Does it make sense? Okay. Is that clear? All right. Now, if the residue happens to be a complex conjugate, happens to be a complex number, can you comment on what happens? Can you comment on the real part of R divided by S minus P1, where R is a complex number? R is a complex number. Earlier we had said 1 by S minus P1. Now the residue could be complex, right? It's some R. So what do you think will happen to the real part of Shravan Siddhartha? What do you think will happen? So what do you think will happen when you have multiple poles, a pole of multiplicity greater than 1? What do you say for this? This is P1, okay, and this is S. So this is S minus P1. All right. So what do you think will happen? 1 by S minus P1 will traverse through P1 whole square, as S traverses through 360 degrees around the pole. 1 by S minus P1 the whole square will go through 720 degrees. So in other words, the number of this will get cut into many sectors, in fact 4 sectors. Correct? Where in here, if S is here, the real part is positive. Real part of what is positive? 1 by S minus P1 the whole square. Then it becomes negative. Okay. Then again it becomes positive, and again it becomes negative. The real part being positive or negative is simply saying whether the argument of 1 by the angle of 1 by S minus P1 the whole square is smaller than 90 degrees or yes, people, come on.
Or in between 90
and 270. If the magnitude of the angle is greater than 90 degrees, then the real part is negative. The magnitude is less than 90 degrees, the real part is positive. Okay. So, those of you, how many of you are able to see this? That as if you have a pole of multiplicity 2, then if you go around the pole, then there will be 4 regions where the real part will alternate between positive and negative. Are you able to see this, or if you are not, please think about it. It's actually pretty straightforward. So now taking this a little further, if the residue was complex, what do you think will happen? These lines will get rotated, but it still follows that you divide space into 4 sectors and the real part becomes positive, negative, positive, negative. Now if you had a pole of multiplicity n, what do you think will happen? It will get divided into 2n sectors, and the real part will keep alternating between positive, negative, and so on. Is this clear? Okay. Now we know that Z of S, we figured out, has a positive real part, has a negative real part here, 0 real part on the j omega axis and positive real part in the right half plane. We know that the poles of Z of S, we are trying to figure out where the poles of, what the constraints are on the poles of Z of S. Can a pole of Z of S lie here? No, why? Because we know that if you go around in the vicinity of a pole, the real part of 1 by S minus P1, which is basically Z of S evaluated at in the neighborhood of P1, right? Its real part is positive in this region and negative here. Does it make sense? Okay, so what is the conclusion? What? This doesn't mean it must lie on the j omega axis. All that it means is that it cannot lie in the left half plane. Is that clear? Yes, I see so many blank faces. Palani Rakesh, what was I explaining? Why can't the pole lie in the left half S plane?
So suppose you calculate the residue of the pole, the real part of 1 by S minus P1. Over this region should be positive and there will be negative.
Which region?
Yeah, near the pole you have a real.
Okay. Alright. If the residue happened to be real for this pole, and if you evaluated Z of S in the neighborhood of P1, then to the right of P1, the real part of 1 by S minus P1, which is also a good approximation to the behavior of Z of S in the neighborhood, right, would have a positive real part on the right and a negative real part on the left. But we know that Z of S must have a negative real part throughout the LHP, which therefore means that you cannot have a pole in the left half plane. So the only place where poles can be must be the imaginary axis. Is this clear? Okay. All right. Now on the imaginary axis, can we have, poles can be multiplicity 1, 2, 3, 4 and so on. Correct? Can we have two coincident poles on the imaginary axis? No. Why? We just saw that if you have poles with the multiplicity greater than 1, then the real part of 1 by S minus P1, right, will alternate positive, negative and so on depending on the multiplicity. But we know that the real part must be positive here and negative here. So what are the conclusions of our analysis? 1, no LHP poles. All right. 2, obviously no RHP poles, and only simple poles on the j omega axis. Correct? Can you comment on the residues of the poles on the j omega axis? The residues must also be positive, because we said that if the residue is some complex number R, then the region over which the real part is positive and negative gets rotated by that angle. Correct? Since the real part must be positive on the right and negative on the left, it must follow that there must be simple poles on the j omega axis, and the residues of these poles must be positive. Is that clear? Okay, we do it outside class.